So, welcome everybody to a new session of the PhD seminar. Today's speaker is Kseniia. She is from the Copenhagen Buissnes School, and she's going to talk us about interpreting clusters by means of mathematical optimization. So, you can start.
Yeah. Thank you very much for inviting me for this seminar. So I really appreciate it because it's a good opportunity to explain your research. And today I'm going to present my working paper, which I'm doing with known for you Emilia Carrizosa and Dolores Romero Morales. And the paper is called Interpreting Clusters by Means of Mathematical Optimization. So on this slide, you can see the outline of presentation. First of all, I'm going to give you some motivation, then introduce the model, give some results, and make a conclusion. So maybe, as you know, I'm sure you know it, machine learning builds mathematical models aimed to extract and represent knowledge from complex data. But there is a problem for some applications, because by using high accuracy machine learning algorithms, we can lose interpretability of results. The good example of it, the comparison of decision trees and random forests. Decision tree is a very interpretable method, but very unstable and has not high accuracy. In comparison, random forest has high accuracy, but unfortunately black box. So the claim of interpretability exists even on the policy level. 2 years ago, the European Union's new general data protection regulation was adopted. Among others, this regulation pressed the importance of human interpretability in algorithmic decision making. So even in this year, also was published white paper about the same claim. So people want to have secure development artificial intelligence. First of all, I want to say that there is no common terminology of interpretability. It could be comprehensibility, transparency, or explanatory power. So I will use some of these words. And there are two ways to aim for interpretability. One way, we can apply a high accuracy method on the first stage and then try to interpret results in the second stage. Or we can incorporate transparency into the decision-making model. They have already done some work on it, and in both cases, mathematical optimization helps to trade off between transparency and accuracy. Our models is in this block, and we inherit some concept of well-known location problems to build our models, and you will see how. So in this presentation, we study the problem of explaining clusters obtained from some clustering procedure, for example, k-means. And we purpose to explain clusters by prototypes, which is our individuals. So we will see further in illustration what is it. And also we have dissimilarity measure between individuals, which is given, and it could be the same dissimilarity which was taken for construct the clusters, or it could be another one, dissimilarity measure, which we think reasonable for our interpretations. And also our explanations could be incorrect for some individuals, and it's how we measure correctly specified and incorrect specified individuals. So let's move to illustration to show it more easier. We have n individuals and C clusters. On this picture we have 2 clusters, red and blue one, and each point it's our individuals. It can be anything. It can be feature, our data, I mean individuals in our data. It can be functions like in functional data, or it could be nodes in graph, but it's more difficult example. And also we have set of candidates to prototype. It's a subset of our individual set, and in general case it's less than our individual set, but it could be also equal to our set of individuals. So then the main question, who of these individuals, we call it prototypes, are going to explain our clusters? Our model gives that answer. Voila. Here we have 2 prototypes which were chosen, and that prototype was chosen for red cluster, that prototype was chosen for blue cluster. I want to mention that for choice, I mean, we can explain our cluster only by individuals who belongs to the same cluster. It's very strange to try explain our cluster by individual from other cluster. So to do so, we are working with dissimilarity measure, and it's given relying on our purpose and data. So it could be any measure which we think could fit for our purpose, but I can give you some example. For example, it can be Euclidean norm for continuous space or something else. So main idea. The model chooses a prototype, like face of our cluster, and assign individuals to chosen prototype. If individual is assigned to prototype from the same cluster, we count it as correct assignment and call it true positives. So look at this picture. Here our chosen prototype, and all individuals who from the same cluster, so red prototype and red individuals, so we count that individuals as true positives. The same for blue cluster. And if an individual is assigned to prototype from another cluster, we count as incorrect assignment and call it false positive. And it could be that some individuals from other cluster will be assigned to prototype for that prototype. Then we should count it like error, like false positives. And also in one model, there could be that individuals are not assigned to any prototype. So we can have individuals from other, I don't know, from here, for example, which are not assigned to that prototype, but we don't count it. Okay, so objective function idea is to maximize total true positive and minimize total false positive across all clusters. So we want to maximize this and this, and minimize this and this, while controlling for the rate of true positives and false positives in each cluster through parameters lambda and mu. And this is our normalized true positive, and this is our normalized false positives. Okay, so we purpose 2 models as mixed integer linear programming model. And as I said in the motivation part, we inherit some concept from location problems, and our model differs in the following. So we use covering approach for one model, which allows to have individuals covered by more than one prototype or not covered at all, and also partitioning approach, which allows to have individuals assigned to only unique prototype. So the partitioning model finds a prototype for each cluster and assigns individuals to each closest prototype. So this guy on this picture was assigned to prototype from red cluster because the dissimilarity measure between these two, between prototype of blue cluster and that guy was larger than this dissimilarity measure. All this assignment is unique, so you can't have assignment to two prototypes. The covering model finds a prototype for each cluster and the radius, and assigns individuals to prototype with which the dissimilarity measure is below than the radius. So it allows us to have, for example, such individuals who assign it to two prototypes, or also allows to have individuals who can be not allowed, not covered at all. Okay, let's move to the formulation of the model. As I said, we introduce our model in mixed integer linear programming problem. We have that variable, we have that binary variable as assignment individuals to prototype. Also, we have that variable as assignment prototype to cluster, and we have continuous radius. And also we know from which cluster our individual is, and we know dissimilarity measure. As I told you, it's given. So, as I said, we maximize total true positives. It is like it looks like, and minimize total false positives with some parameter. Then we have to ensure that we choose one prototype per cluster. Then we have to assign it our individuals to chosen prototype, and it's actually big M constraint. So, but in real life, this M is known. We can take relying on our data some number. Then, as I said, we have to control total number, not total rate of true positives, and it's our lambda, and rate of false positives, and add some integer constraints and radius bounds. So, as you can see, here we have multiplication of two decision variables, which means that our model is bilinear, but we can eliminate it by applying Fortet transformation. So we introduce new variable and add new constraints. Then the final model is mixed integer linear programming model with such numbers of binary decision variables and constraints. And I want to mention that the size of that model is quadratic in number of individuals for binary decision variables and for constraints. So it's quite large. Okay, so there's some properties of the covering model which can be useful. First of all, it could be that clusters which we have different sizes. Then it's a good idea to reformulate that model for each cluster separately, which allow us to have different radiuses and different quality lambda and mu. So then imagine that we have first model was like 3 clusters, but then we reformulated for each cluster separately, and we consider like one cluster against of all others clusters. So it's and then we have different radius for each cluster. Also, instead of considering continuous radius, we can consider set of discrete set of radius. And then problem becomes easier, but we have to selection of models with fixed radius. And also the model can be extended to have more than one prototype per cluster. Okay, very quick about the partitioning model. We have again decision variable for assignment to individual to prototype, decision variable to choice of prototype for cluster. We have our data and yeah, one extra set. So here could be the same objective function, but I put epsilon equal to 0, and so this objective function is maximizing only of total true positives. It's possible, one possible case. And what also differ from the covering model, this model is only for unique assignment. So we change our allocation of individuals to prototypes, and also we don't have any radius here. Again, we control true positives and false positives and some integer constraints. And this model, sorry, is also nonlinear. Yeah, and we have to add some to do Fortet transformation. Yeah, but we are not focused on this model a lot. Okay, so let's move to results. We provide some results for real-life functional data and for the simulated data. We solve these models by using Groby software with Python, and here's my computer. I don't know, is it useful information or not, but maybe just to imagine what kind of, how large problem can I solve on my computer. Okay, here's our functional data. What do you think? What is it? I know you are muted now, so I will skip this question. And here I add some colors. I also know that for some of you it's a known data set. It's Canadian climate data, contains daily time series for temperature for 35 cities grouped for climates. So it's actually temperature in 1 year. And we use as the similar measure Euclidean norm between time series and plus Euclidean norms of time series differences of period 1. So we take this, actually it's vector or length of 365, and then compute Euclidean norm, like difference between two vectors, and then Euclidean norm of it. And also difference, it's like we take 1 day minus second day, it's one observation, second day minus third day, then we construct a new vector of 364 observations, and also consider Euclidean norm of it. So we apply for that model separate covering model, due to our clusters are very unbalanced. We have, for example, one cluster with 3 observation and with 15 observation, another one. And for some of them, we get very good, you can see it, sorry, it's very small, but I will say you that, for example, for that cluster, we have very good quality of explanations, because it's 100% of true positives and 0% of false positives. So we explain our cluster without any errors. And yeah, I want to also say that these bold lines, it's our prototypes, which was chosen as prototype which can explain our cluster. And if you see another one colors, it's errors which we get by by solving our model. Errors in terms of explanations. Okay, maybe on the simulated data it's going to be easier to understand. We construct simulated data in two-dimensional space with Euclidean distance because it's easier to visualize what's going on in our model. Then we can build 1,500 of individuals grouped in 6 clusters, which are like this one on this picture. And let's look at the results. Voila. So because of Euclidean distance, we can easily draw these circles. And I want to highlight that our model was solved for separately for each cluster. And for example, you can see here all true positives and false positives. For example, for this blue cluster, we see that all individuals of blue cluster inside of the ball, then all blue points is true positives. And then we can see how much individuals from other cluster were also covered by this circle, and it's our false positives. And the same for all clusters. So, and quality of this model actually quite good. Okay, but could we do more? Because, as I said, it's quadratic in the size of problem is quadratic in n. So it's like this number in square of binary variables, and the same for constraint. So it's quite large. But we can apply this result for larger problem. Imagine that this problem were subsample of bigger problem, for example, for 6,000 individuals. And because we can calculate how good we are and how bad we are by just looking how much individuals from new data appears here, and how much individuals we lose from new data here, then we can get this quality for new data, and we call it actual lambda mu, and it's also quite high. So we can simply use subsampling for larger problem. And it's very natural to have balance of lambda and mu, because we try to maximize true positives and minimize false positives. So there is a trade-off between these two values. And for example, on this picture, on this graph, you can see how these two values behave against each other, relying on our simulated data. And for example, you can have 100% of true positives with very small false positives. So it's I know that data is quite good for simulated data is quite good, and yeah, we can see it on this graph. Okay. Also, I told you that we can extend our model for more prototypes per cluster. And look at this picture. We just try to imagine what kind of, if we would like to cover, for example, blue prototype, of course, we can easily do it with one prototype and one circle. But for red cluster, which is our border, we can't do this easily. So we need to extend our model for that red cluster. And let's see what we get. Voila. So we're importing 8 prototypes for red one and 1 prototype for blue one. I know that it seems to be very easy because you can do it on hand, but imagine that we have data, high dimensional data, and then you can't visualize it. And I mean that for more complex data, of course you can't do this, but we provide this example just for showing how our model works. Okay, so that's it for my result part. In conclusion, I want to mention again, we built several mathematical optimization models in order to deliver annotations of clusters by so-called prototypes. So we explain our cluster by some individuals, which is space of our cluster, and we provide results for real-life data and for simulated data. And as extent for this model, we are going to try incorporate, as I said in the very beginning, clustering procedure into the mathematical optimization problem. So I'm thinking I'm quite fast. Thank you for your attention. So there's in the rest 3 lists of references. Okay, I don't know how to move further. I'm here and I'm ready to hear from you something.
Thank you, Kseniia.
Yeah.
Does anyone have a question or?
Yeah, maybe I was too quick. Yeah.
No, it was fine. So, Vanessa?
Hello, can you hear me?
Yes.
Yeah, hi.
Hi, I'm very happy to hear you and see you.
You too, you too.
It was a very interesting talk, and you have explained everything in a very clear way, so that's something which is very nice.
Yep.
So I had a couple of questions for you. Actually, you have already answered one of them, which is actually one of your future lines of research. Because I was thinking about integrating the interpretability together with the clustering, no? So I guess that, yeah. So.
Yeah. There is, yeah, of course, it's good goal. I mean, to have both in one model. But if you ask me why not to do it immediately, I mean, skipping this step, I would say that probably, yeah, if we apply a high accuracy method on first stage, maybe we can get better accuracy and then interpret it. Maybe our goal just to understand the method or our data. Then it's better maybe to apply this method. And if, but if you want to have clustering with interpreting with transparency, then it's better, of course, to use that method. I mean, if it wasn't your question, but to clarify.
No, but yes, I understand your point. In the end, you have started, let's say, from the very beginning, and then you can extend, of course, this idea to more general approach, of course. And maybe what I'm going to say now doesn't make sense at all, but I was thinking about the prototypes obtained with k-medioids, the classical algorithm. So I was thinking whether it makes sense to compare somehow the prototypes that you obtain with your approach with the ones that you will get using this classical method.
Yeah, it's a good point. Because I know what you mean. Because
because with K means the prototype that you obtain is not really an observed individual, no? But with the other one, his brother or sister, whatever you want to say, medioid.
Yeah. But here's another one issue, because in k-medioids, you're not so flexible in in comparison your cluster with other cluster. Because in our model, for example, you always compare these two clusters and try to choose something which is similar to your own cluster, but more dissimilar to other cluster. And we can control it by our lambda mu. And also, as I told you on the very beginning, we can use another dissimilarity measure. So, yeah, because you can use all data which you have for building clusters, but then you just want to explain these clusters by very special features which you have in your data, and then
yes, of course, it is much more general, no, than this idea. That's why I'm sure that if you are able to obtain somehow a way to compare them, your approach will beat the K-mediate. So that was my idea. So
yeah, good idea. Thank you. We didn't think about it. Yeah, but good idea.
Okay. So thank you very much again.
Thank you. Thank you.
Any other question?
I think no question. Sandra, you told me that you will ask me something.
What? Wait.
Okay.
My God. I am not sure if you have explained that with the radius of, the circles that you create or not, but it can be some problems of infeasibility regarding the values of lambda mu, or?
Yeah. Yeah. Of course. I mean that for some data you can cover all points without huge error, but for some data you can't do this and you will have some errors. So our lambda and mu is parameter which we put in the beginning of the model, so it's given value, and yeah, it's how we measure our quality. That's it. It's not something which we can just suggest what kind of a lambda and mu we will have, but we will see, do we have feasible solution or not. But you're right, for some lambda and mu, for example, for 0 lambda, for some lambda and mu, you can't have any solutions. It's true. And for some radiuses, it's correct. And
following this question, I was going to ask you if you plan to solve this problem of infeasibility using, for example, a grid of values in lambda mu, or?
So, what could you please again? What do you mean infeasibility?
To be, I mean, the problem is impossible to solve because you are imposing too much performance.
Okay. For some data, I mean, I even can build some data in my mind, which will be impossible to solve with high lambda and low mu. So, but if you ask to solve model very poor, for example, with 50% and 50% here, so maybe it's quite easy to do.
Yeah.
But it's I mean, it's applications. It's more about data which you have. It's not about the model.
Yeah.
So we are trying to find. We're trying to prove something for feasibility, but of course, not all lambdas and mu allow us to have it. Yeah.
Okay, thank you.
You're welcome. Yeah. So, if no question, I don't know, maybe I can speak with you without any share screen, and yeah, maybe it's better. So, I don't know. Okay.
Any question or we can finish?
Yeah.
Okay, so I think that people are leaving, so we can finish. Thank you so
Yeah.
much, Kseniia.
Thank you very much for giving this opportunity, and I'm very happy to see you again. Yeah,
The
maybe.
same.
Yeah, maybe next year we will meet each other personally.
Yeah, yes, it's better.
Yeah.
Okay, thank you so
Thank
much.
you. Thank you. Thank you. Bye. Bye.
Bye.